z squared. Now I'm going to expand these. You can expand it any way you like, using Pascal's triangle or just by knowing how they expand. But they will expand to z cubed minus 3z plus 3 over z minus 1 over z cubed, all multiplied by z squared plus 2 plus 1 over z squared. Now, multiplying these out, I'm going to z cubed times z squared is going to give me z to the fifth, and by the magic of this method, of course, my minus 1 over z cubed times my 1 over z squared there gets me minus 1 over z to the fifth. Very important at this point to make sure you're tracking the negatives and positives and getting them correct. Now that is then going to be, I'm then going to subtract z cubed minus 1 over z cubed. So I'm expanding these out and doing a fair bit of simplification in the middle. That z cubed there comes from the fact that you've got z cubed times 2, you've got 2 z cubes there, but you're going to lose minus 3z cubed from this, so you end up with minus 1z cubed. You can either believe me this expands like this, or do the layer of proper working in the middle and see how it all simplifies down to this level. Then we end up with minus 2z minus 1 over z. As I say, if you're not certain about that, and expand all of these out carefully and see how they add and subtract to end up with this nice little pattern here. Now, at this point, I need to then start dealing with these 2i cubed and 2 squared there, and this is going to get me sine cubed cos squared theta at this point is going to equal, now if I divide through, now that 2 cubed there is 8 and that 2 squared is 4, so I've got 32 at this point. So I end up with minus 1 over, using the hint from the question that we're expecting a 16th here, I've got a 16th in there, and I know I need 32, so I'm going to end up with 1 over 2 there. But of course, I've got to deal with that I cubed there. Now I cubed is minus I, and that's where that minus came from there. But I end up with 1 over 2i here into my z to the fifth minus 1 over z to the fifth minus 1 over 2i here, z cubed minus 1 over z cubed minus and 2 over 2i z minus 1 over z. And this structure here, 1 over 2i z to the fifth minus 1 over z to the fifth, is sine 5 theta. If you do a similar expansion of if you were to do cos 5 theta plus I sine 5 theta, it's then equal to z to the fifth. You'll see where that comes from, but it's one of the standard results, one of the standard technique, and the examiner's going to be perfectly happy if you just step from there to sine 5 theta. So we end up with minus 1 over 16 sine 5 theta. Then likewise, 1 over 2i z cubed minus 1 over z cubed is going to be sine 3 theta. And at the end here, well, minus 2 over 2i is then going to be 2, because 1 over 2i z minus 1 over z would be sine 2 theta, but we've got 2 of them, so we end up with 2 sine 2 theta at this point. And which was the result that we were meant to prove. Now, part 2 then asks us to hence show that all the roots of the equation sine 5 theta equals sine 3 theta plus 2 sine theta are of the form theta equals n. So let's write this down. So sine 5 theta equals sine 3 theta plus 2 sine theta. We need to show that all the roots are of the form theta equals n pi over k, where n is any integer and k is to be determined. So we can rearrange this equation to look like our identity that we just created. So we can write sine 5 theta minus sine 3 theta minus 2 sine theta equals 0, and then use our identity to convert that to minus 16 sine cubed theta cos squared theta, because we know that if we were to multiply up by 16 at this point, that's what we'd get, and make that equal to 0. Now, divide through by minus 16 to make things a bit easier, and I've got sine cubed theta cos squared theta equals 0. Now, roots of this, if sine theta is 0, then this is going to be true. So sine theta equals 0, or if cos theta equals 0. Both of those situations are going to give me these roots. Now, for sine theta to equal 0, that means theta is going to be some multiple of pi, possibly 0 if r is 0. And for cos theta to equal 0, then theta is going to have to be 2r plus 1 times pi by 2, so it's a little more complicated because cos theta is 0 at each alternate. Let's sketch it and see, show you what I mean. So you've got pi by 2 there, haven't you? And that on 3 pi by 2, and so on, and then you've got pi in the middle. So when r is 0, you get this first root here. When r is 1, you get the 3 pi, and so on. So that's where, so under these two situations, this is true. And if we combine these two together, so at every r and every 2r plus 1, you can see that when r is 0, then we get sine theta 0. When r is 1, then we're going to get, in here, if r was 1, we get 3 pi by 2, and it's 0 again. If r is 2, and so on, we're going to get 2 pi, then sine theta 0, and cos theta 0, and so on. And it will, sorry, no, at r is 2, sine theta kicks in as 0. When r is 3, then cos theta 0, and so on. So for, in fact, they are the form n pi by 2. So every multiple of pi by 2, the equation is 0. Yeah. And so if we then, so this is for n is equal to 0, 1, 2, and so on. So they then asked us to show what that n was any integer, and that means in their equation k is equal to 2 as well. And so theta is of the form theta equals n pi by k, where n is any integer and k is equal to 2. And that's the end of question 5.